Chapter 4. Drug Biotransformation. Why is drug biotransformation necessary? The mammalian drug biotransformation systems are thought to have first evolved from the need to detoxify and eliminate plant and bacterial bioproducts and toxins, which later extended to drugs and other environmental xenobiotics. Renal excretion plays a pivotal role in terminating the biologic activity of some drugs, particularly those that have small molecular volumes or possess polar characteristics, such as functional groups that are fully ionized at physiologic pH. However, many drugs do not possess such physicochemical properties. Pharmacologically active organic molecules tend to be lipophilic and remain unionized or only partially ionized at physiologic pH. These are readily reabsorbed from the glomerular filtrate in the nephron. Certain lipophilic compounds are often strongly bound to plasma proteins and may not be readily filtered at the glomerulus. Consequently, most drugs would have a prolonged duration of action if termination of their action depended solely on renal excretion. An alternative process that can lead to the termination or alteration of biologic activity is metabolism. In general, lipophilic xenobiotics are transformed to more polar and hence more readily excreted products. The role that metabolism plays in the inactivation of lipid-soluble drugs can be quite dramatic. For example, lipophilic barbiturates such as thiopental and pentobarbital would, normal values are in parentheses, have extremely long half-lives if it were not for their metabolic conversion to more water-soluble compounds. Metabolic products are often less pharmacodynamically active than the parent drug and may even be inactive. However, some biotransformation products have enhanced activity or toxic properties. It is noteworthy that the synthesis of endogenous substrates such as steroid hormones, cholesterol, active vitamin D congeners, and bile acids involves many pathways catalyzed by enzymes associated with the metabolism of xenobiotics. Finally, drug metabolizing enzymes have been exploited in the design of pharmacologically inactive prodrugs that are converted to active molecules in the body. The role of biotransformation in drug disposition. Most metabolic biotransformations occur at some point between absorption of the drug into the circulation and its renal elimination. A few transformations occur in the intestinal lumen or intestinal wall. In general, all of these reactions can be assigned to one of two major categories called phase I and phase II reactions, Figure 4:1. Phase I reactions usually convert the parent drug to a more polar metabolite by introducing or unmasking a functional group O and H2SH. Often these metabolites are inactive, although in some instances activity is only modified or even enhanced. If phase I metabolites are sufficiently polar, they may be readily excreted. However, many phase I products are not eliminated rapidly and undergo a subsequent reaction in which an endogenous substrate such as glucuronic acid, sulfuric acid, acetic acid, or an amino acid combines with the newly incorporated functional group to form a highly polar conjugate. Such conjugation or synthetic reactions are the hallmarks of phase II metabolism. A great variety of drugs undergo these sequential biotransformation reactions, although in some instances, the parent drug may already possess a functional group that may form a conjugate directly. For example, the hydrazide moiety of isoniazid is known to form an acetyl conjugate in a phase II reaction. This conjugate is then a substrate for a phase I-type reaction, namely, hydrolysis to isonicotinic acid, Figure 4:2. Thus, phase II reactions may actually precede phase I reactions. Where do drug biotransformations occur? Although every tissue has some ability to metabolize drugs, the liver is the principal organ of drug metabolism. Other tissues that display considerable activity include the gastrointestinal tract, the lungs, the skin, the kidneys, and the brain. After oral administration, many drugs, isoproterenol, meperidine, pentazocine, morphine, are absorbed intact from the small intestine and transported first via the portal system to the liver, where they undergo extensive metabolism. This process is called the first-pass effect, see Chapter 3. Some orally administered drugs, clonazepam, chlorpromazine, cyclosporine, are more extensively metabolized in the intestine than in the liver, while others, midazolam, undergo significant, 50%, intestinal metabolism. Thus, intestinal metabolism can contribute to the overall first-pass effect, and individuals with compromised liver function may rely increasingly on such intestinal metabolism for drug elimination. Compromise of intestinal metabolism of certain drugs, felodipine, cyclosporine A, can also result in significant elevation of their plasma levels and clinically relevant drug-drug interactions, DDIs, see below. First-pass effects may limit the bioavailability of orally administered drugs, lidocaine, so greatly that alternative routes of administration must be used to achieve therapeutically effective blood levels. Furthermore, the lower gut harbors intestinal microorganisms that are capable of many biotransformation reactions. In addition, drugs may be metabolized by gastric acid, penicillin, by digestive enzymes, polypeptides such as insulin, or by enzymes in the wall of the intestine, symport-emetic catecholamines. Although drug biotransformation in vivo can occur by spontaneous, non-catalyzed chemical reactions, most transformations are catalyzed by specific cellular enzymes. At the subcellular level, these enzymes may be located in the endoplasmic reticulum, mitochondria, cytosol, lysosomes, or even the nuclear envelope or plasma membrane. Microsomal mixed function oxidase system and phase I reactions. Many drug metabolizing enzymes are located in the lipophilic endoplasmic reticulum membranes of the liver and other tissues. When these lamellar membranes are isolated by homogenization and fractionation of the cell, they reform into vesicles called microsomes. Microsomes retain most of the morphologic and functional characteristics of the intact membranes, including the rough and smooth surface features of the rough, ribosome-studded, and smooth, no ribosomes, endoplasmic reticulum. Whereas the rough microsomes tend to be dedicated to protein synthesis, the smooth microsomes are relatively rich in enzymes responsible for oxidative drug metabolism. In particular, they contain the important class of enzymes known as the mixed-function oxidases, MFOs, or monoxygenases. The activity of these enzymes requires both a reducing agent, nicotinamide adenine dinucleotide phosphate, NADPH, and molecular oxygen. In a typical reaction, one molecule of oxygen is consumed, reduced, per substrate molecule, with one oxygen atom appearing in the product and the other in the form of water. In this oxidation-reduction process, two microsomal enzymes play a key role. The first of these is a flavoprotein, NADPH cytochrome P450 oxidreductase, POR, or CPR. 1 mole of this enzyme contains 1 mole each of flavin mononucleotide, FMN, and flavin adenine dinucleotide, FAD. The second microsomal enzyme is a hemoprotein called cytochrome P450, which serves as the terminal oxidase. In fact, the microsomal membrane harbors multiple forms of this hemoprotein, and this multiplicity is increased by repeated administration of or exposure to exogenous chemicals. See text that follows. The name cytochrome P450, abbreviated as P450 or CYP, is derived from the spectral properties of this hemoprotein. In its reduced, ferrous, form, it binds carbon monoxide to give a complex that absorbs light maximally at 450 nanometers. The relative abundance of P450S, compared with that of the reductase in the liver, contributes to making P450 heme reduction a rate-limiting step in hepatic drug oxidations. Microsomal drug oxidations require P450 reductase, NADF, and molecular oxygen. A simplified scheme of the oxidative cycle is presented in Figure 4-3. Briefly, oxidized, Fe+3. P450 combines with a drug substrate to form a binary complex. Step 1. NADF donates an electron to the flavoprotein P450 reductase, which in turn reduces the oxidized P450 drug complex. Step 2. A second electron is introduced from NADF via the same P450 reductase, which serves to reduce molecular oxygen and to form an activated oxygen P450 substrate complex. Step 3. This complex in turn transfers activated oxygen to the drug substrate to form the oxidized product. Step 4. The potent oxidizing properties of this activated oxygen permit oxidation of a large number of substrates. Substrate specificity is very low for this enzyme complex. High lipid solubility is the only common structural feature of the wide variety of structurally unrelated drugs and chemicals that serve as substrates in this system. Table 4:1. However, compared with many other enzymes including phase 2 enzymes, P450s are remarkably sluggish catalysts, and their drug biotransformation reactions are slow. Human liver P450 enzymes. Gene arrays combined with immunoblotting analyses of microsomal preparations, as well as the use of relatively selective functional markers and selective P450 inhibitors, have identified numerous P450 isoforms, CYP, 182, 2A6, 2B6, 2C8, 2C9, 2C18, 2C19, 2D6, 2E1, 3A4, 3A5, 4A11, and 7, in the human liver. Of these, CYP182, CYP2A6, CYP2B6, CYP2C9, CYP2D6, CYP2E1, and CYP3A4 appear to be the most important forms, accounting for approximately 15%, 4%, 1%, 20%, 5%, 10%, and 30%, respectively, of the total human liver P450 content. Together, they are responsible for catalyzing the bulk of the hepatic drug and xenobiotic metabolism. Table 4:2, Figure 4:4. It is noteworthy that CYP3A4 alone is responsible for the metabolism of over 50% of the prescription drugs metabolized by the liver. The involvement of individual P450s in the metabolism of a given drug may be screened in vitro by means of selective functional markers, selective chemical P450 inhibitors, and P450 antibodies. In vivo, such screening may be accomplished by means of relatively selective non-invasive markers, which include breath tests or urinary analyses of specific metabolites after administration of a P450 selective substrate probe. Enzyme induction. Some of the chemically dissimilar P450 substrate drugs, on repeated administration, induce P450 expression by enhancing the rate of its synthesis or reducing its rate of degradation. Table 4:2. Induction results in accelerated substrate metabolism and usually in a decrease in the pharmacologic action of the inducer and also of co-administered drugs. However, in the case of drugs metabolically transformed to reactive metabolites, enzyme induction may exacerbate metabolite-mediated toxicity. Various substrates induce P450 isoforms having different molecular masses and exhibiting different substrate specificities and immunochemical and spectral characteristics. Environmental chemicals and pollutants are also capable of inducing P450 enzymes. Exposure to benzopyrene and other polycyclic aromatic hydrocarbons, which are present in tobacco smoke, charcoal broiled meat, and other organic pyrolysis products, is known to induce CYP1A enzymes and to alter the rates of drug metabolism. Other environmental chemicals known to induce specific P450S include the polychlorinated biphenyls, PCBs, which were once used widely in industry as insulating materials and plasticizers, and 2,3,7,8 tetrachlorobenzopdioxin, dioxin, TCDD, a trace byproduct of the chemical synthesis of the defoliant 2,4,5T, see Chapter 56. Increased P450 synthesis requires enhanced transcription and translation along with increased synthesis of heme, its prosthetic cofactor. A cytoplasmic receptor, termed A, for polycyclic aromatic hydrocarbons, EG, benzoapyrene, dioxin, has been identified. The translocation of the inducer receptor complex into the nucleus, followed by ligand-induced dimerization with UNT, a closely related nuclear protein, leads to subsequent activation of regulatory elements of CYP1A genes, resulting in their induction. This is also the mechanism of CYP1A induction by cruciferous vegetables, and the proton pump inhibitor, omeprazole. A pregnenin X receptor, BXR, a member of the steroid retinoid thyroid hormone receptor family, has recently been shown to mediate CYP3A induction by various chemicals, dexamethasone, rifampin, mifepristone, phenobarbital, atorvastatin, and hyperforin, a constituent of St. John's wort, in the liver and intestinal mucosa. A similar receptor, the constitutive androsten receptor, CAR, has been identified for the relatively large and structurally diverse phenobarbital class of inducers of CYP2B6, CYP2C9, and CYP3A4. Paroxysm proliferator receptor, PAR, is yet another nuclear receptor highly expressed in liver and kidneys, which uses lipid-lowering drugs, EG, fenofibrate and gemfibrozil, as ligands. Consistent with its major role in the regulation of fatty acid metabolism, PAR mediates the induction of CYP4A enzymes, responsible for the metabolism of fatty acids such as arachidonic acid and its physiologically relevant derivatives. It is noteworthy that on binding of its particular ligand, BXR, CAR, and PAR each forms heterodimers with another nuclear receptor, the retinoid X receptor, RXR. This heterodimer in turn binds to response elements within the promoter regions of specific P450 genes to induce gene expression. P450 enzymes may also be induced by substrate stabilization, EG, decreased degradation, as is the case with trulendomycin or clotrimazole-mediated induction of CYP3A enzymes, the ethanol-mediated induction of CYP2E1, and the isosafrole-mediated induction of CYP1A2. Enzyme inhibition. Certain drug substrates inhibit cytochrome P450 enzyme activity, Table 4-2. Imidazole-containing drugs such as cimetidine and ketoconazole bind tightly to the P450 heme ion and effectively reduce the metabolism of endogenous substrates, EG, testosterone, or other co-administered drugs through competitive inhibition. Macrolide antibiotics such as trulendomycin, erythromycin, and erythromycin derivatives are metabolized, apparently by CYP3A, to metabolites that complex the cytochrome P450 heme ion and render it catalytically inactive. Another compound that acts through this mechanism is the inhibitor proadifin, SKF 525A, used in research, which binds tightly to the heme ion and quasi-irreversibly inactivates the enzyme, thereby inhibiting the metabolism of potential substrates. Some substrates irreversibly inhibit P450S via covalent interaction of a metabolically generated reactive intermediate that may react with the P450 apoprotein or heme moiety, or even cause the heme to fragment and irreversibly modify the apoprotein. There Antibiotic chloramphenicol is metabolized by CYP2B1 to a species that modifies the P450 protein and thus also inactivates the enzyme. A growing list of such suicide inhibitors, inactivators that attack the heme or the protein moiety, includes certain steroids, ethanylestradiol, norethindrone, and spironolactone, fluoroxine, alabobital. The analgesic sedatives allylisopropyl lura, diethylpentanamide, and ethylflavanol, carbon disulfide, grapefruit furanocoumarins, selagiline, phencyclidine, taclopidine and clopidogrel, ritonavir, and propylthiouracil. On the other hand, the barbiturate secobarbital is found to inactivate CYP2B1 by modification of both its heme and protein moieties. Other metabolically activated drugs whose P450 inactivation mechanism is not fully elucidated are mifepristone, droglitazone, raloxifene, and tamoxifen. Phase 2 reactions. Parent drugs or their phase I metabolites that contain suitable chemical groups often undergo coupling or conjugation reactions with an endogenous substance to yield drug conjugates. Table 4-3. In general, conjugates are polar molecules that are readily excreted and often inactive. Conjugate formation involves high-energy intermediates and specific transfer enzymes. Such enzymes, transferases, may be located in microsomes or in the cytosol. Of these, iridine 5-diphosphate, UDP glucuronyl transferases, UGTs, are the most dominant enzymes, figure 4-4. These microsomal enzymes catalyze the coupling of an activated endogenous substance, such as the UDP derivative of glucuronic acid, with a drug, or endogenous compounds such as bilirubin, the end product of heme metabolism. 19 UGT genes, UGT1 and UGT2, encode UGT proteins involved in the metabolism of drugs and xenobiotics. Similarly, 11 human sulfotransferases, SULTs, catalyze the sulfation of substrates using 3-phosphoadenosine 5-phosphosulfate, PAPS, as the endogenous sulfate donor. Cytosolic and the microsomal glutathione, GSH,